In this lesson, we're going to discuss one-sided limits. The learning outcomes for this section are define one-sided limits and provide examples, explain the relationship between one-sided and two-sided limits. If you recall earlier in this chapter, we talked about three functions. We talked about g of x equals absolute value of x minus 2 over x minus 2. And if you recall, that graph had something. Let's see if I can go to my draw screen there. Graph looks something like, let me get this here. Not great lines, but here we go. At 2 is where the change occurred, and it looked something like this. It was open circle there, and it was open circle there, and it went back that way. So as x is bigger than 2, the function produced a 1. If x was less than 2, the function produced a negative 1. And so we decided the limit does not exist because these limits are not the same as they approach the value 2. The limit at 2 does not exist because these functions do not go to the same value. But we do have what we call one-sided limits, a limit on each side. So if we look at the limit from the left side, it's at negative 1, and the limit from the right side is at positive 1. And so there's a certain notation here that we have for that. And I want to be very clear about this. Some people get the notation a little confused. So this notation means the limit of g of x as x approaches 2 with a minus sign there means from the left side. So also called from the negative side, but it's from the left side. Whereas if you want to get it from the right side, it'd be the limit. Can anyone guess what this would be? Of g of x equals 1. That's as x approaches 2 from the right side, we put a little plus. So the left side has that minus there, and the right side has the plus. And that's how we distinguish which side of the particular value we're working with it's going to be. There it is from the right side. So here's our formal definition. We define two types of one-sided limits. Limit from the left. Let f of x be a function defined at all values in an open interval of the form CA, and let L be the real limit, or a real number. If the values of the function f of x approach the real number L, as the values of x, where x is less than a, approach the number a, then we say that L is the limit of f of x as x approaches a from the left. Symbolically, we express the idea as, and that's what we saw before, limit of f of x as x approaches a from the left, the little negative thing means from the left, then that equals L. Limit from the right, let f of x be a function defined at all values in an open interval of the form a, c, and let L be a real number. If the values of the function f of x approach the real number L as the values of x, where x is greater than a, approach the number a, then we say that L is the limit of f of x as x approaches a from the right. Symbolically, we express the idea again as limit of f of x as x approaches a from the right, the plus means from the right, equals L. So evaluating, let's try an example here, evaluating one-sided limits. So in this case here, if you notice, we're looking at the limits as they approach 2. 2 is where this change occurs in this piecewise function. So if we're looking at limit as x approaches 2 from the left side, we're going to be looking at the first part. So the limit as x approaches 2 from the left side of f of x is considering basically the limit as x approaches 2 from the left side of x plus 1. And if we put the 2 in there, we'll end up with 2 plus 1, which is 3. Then if we look at it from the right side, the limit as x approaches 2 from the right side of f of x is essentially looking at the limit as x approaches 2 from the right side of x squared minus 4. So that's going to be 2 squared minus 4, which is 0. And our graph of that, if we want to see a graph, let me give you a little rough graph. At x squared minus 4 is going to be a parabola that at 2 it's going to start out at 0. And the other one's x plus 1. So let me go ahead and plot some points here. Let's see here. At 2, that would have been at 3. So I'm going to do an open circle here at 3 because for the left-sided one, it's not included. And then our slope is, so at 1, it's going to be 2. I guess that 3 is not quite a 3, is it? Put up there a little more. And then there. And then at 0, it's at 1. So it looks something like this. And the other one, it'd be a parabola that would have gone down to -4, but it picks up with this piecewise function there. Something like that. So there's our graph. We can see the left side and the right side graphs. I hope that helps. And there's a video for you to watch if you want to see that video in the homework in the book, online book. So use the table of functional values to estimate the following limit if possible. So we want to look at the limit as x approaches 2 from the left side of the absolute value of x squared minus 4 over x minus 2. Now we saw this earlier, and hang on, with this problem here. And so if we're looking at it from the left side, we're going to be looking at this part over here from the left side as it approaches 2 from the left side. And this one has a limit of, as we saw earlier, -4. But from the right side, this has that limit of 4. So this one has the limit of -4, whereas from the right side, it has the limit of +4. And that goes back to the graph that we just did on Desmos. Okay, let's look at this problem. The graph below is the function y equals f of x. So we're going to fill in the values. What is f of 1? Well, we look for 1 for the x value, and what is the corresponding y? Wouldn't be the open circle, it's going to be down here. So that looks like -1. What is the limit as x approaches 2 of f of x? So here's 2. So from one direction, it's approaching 1, and the other direction, it's approaching 1. So since both directions is approaching 1, it's going to be 1. What's the limit as x approaches 1 of f of x? So here's 1. Now, from the right side, it's approaching 2. From the left side, it's approaching -1. And since it's approaching different values, that limit does not exist because it's asking for the overall limit. So we'd say it does not exist. However, if you look at it, now we're on -1. The limit as x approaches -1 from the right. So from the right, it's this direction here. So we're going along this path here. And then that's our value there. So it'll be 1. As x approaches 1 from the left, this is approaching 1 from the left, we're going to get that. But it's f of x plus 2. So if I were to put that 1 in there, so 1 plus 2 is 3. So imagine approaching 3 from the left. it's going to be up here at 2. So we're talking about this up here because that x plus 2. Okay, one more. What is f of 1.5 plus h minus f of 1.5 all divided by h as h goes to 0? So that's an interesting question, and this actually gets a little preview of the definition of a derivative when we find out with the limit process. If you recall, when we talked about a derivative in our first lesson, we talked about it being a slope. So, and we want to know what that slope is as we get closer and closer to the point. So think about x being 1.5, do this in red here, and so it's up along this direction. And they're saying that 1.5 plus h. H is some unknown value, but it's going to be, assume it's something in this area, and it's getting closer and closer to 0, so we're talking about two values getting close together here. So essentially we're trying to find the slope at this point x being 1.5. So it's the slope that we're after here with that type of notation and that calculation, where h is becoming closer and closer to 0 means the 2 points getting closer together. So in essence, what is the slope of this line here? So our slope is going to be, well, we can take some points there. Looks like that line goes through 1, 2, and it goes through 2, 1. And so we just do some quick math here. 2 minus 1 over 1 minus 2, 1 over negative 1 or negative 1. So our slope there is a negative 1, because that function is talking about the slope at that point where x is 1.5. And the y is the corresponding y value, which actually is 1.5 as well. Okay, hope that makes some sense. So now let us consider the relationship between the limit of a function and a point, and the limits from the right and left sides of that point. It seems clear that if the limit from the right and the limit from the left have a common value, then that common value is going to be the limit of the function of the point, which is true. Similarly, if the limit from the left and the right take on different values, the limit does not exist. So this gives us this relating one-sided and two-sided limits. Let f of x be a function defined at all values in an open interval containing a, except possibly at a itself. And let L be a real number, then the limit as x approaches a of f of x equals L, if and only if. If and only if means both these conditions must apply. The limit as x approaches a from the left of f of x is L, and the limit as x approaches a from the right of f of x equals L. So if they equal the same thing, then your function is going to work. Now, also if and only if means this. If the second part is true, the first part's true. If the first part's true, then the second part's true. So that's the if and only if statement. It's an if, then in both directions. Okay, let's go on to the next. So here we have the limit as x approaches 3 from the left of f of x is 1, and the limit as x approaches 3 from the right of f of x is 1. So given the following one-sided limits, does the two-sided limit exist? Well, since they are both equal the same thing, the answer is yes. And that would do it for this section, I believe. Okay.